So friends, today we will discuss about the reliability concepts. So reliability is basically the new term normally, and it is better than quality. So normally we are giving the reliability in form of warranty, specifically when we are going for purchasing the new product. So how we can decide the reliability is that just you have to see it is a kind of property that a system or product will perform in a satisfactory manner for a given percentage of time. So we have to decide a period of time to which a particular process runs or particular parts runs under specific operating conditions. So you have to keep in mind about the operating condition. Specified operating condition is one of the most important things under uh, with respect to time. So whenever you are deciding a particular product to be performed satisfactorily for a given period of time under a specified operating condition, then we have to decide the reliability. And reliability is normally not an absolute number, but it is the probability. We have to measure the reliability in terms of probability, like 10%, 20%, or say 50%, a kind of thing is there. So how or why this topic is one of the most important thing is that normally it is better than quality, because quality gives only standards how a particular product is complete in a specific operation, but reliability adds satisfactory performance, so it is better than quality. And you have to measure, you have to normally industries are giving the reliability in terms of warranty, we are calling it as. So warranty is nothing but a kind of reliability, we can call it as. Now we have to see that how we can decide is reliability. So what are the different elements of reliability that we have to see here? So reliability elements are like we can see the probability is one of the important element in which, or it is a numerical number through which we can define the reliability. Also second important element is satisfactory performance. So this is the criteria over which we have to decide the a particular system or a particular product is performed in satisfactory way. So these are the components of reliability that you have to see. Then another components are specified time. So third important component is specified time. So we have to decide the prerequisite time over which a particular product or system or service is continuously performing. For example, we are purchasing the television, then they are giving us 1 year warranty. For example, say we have to purchase the mobile, then we have given the warranty of 1 year. So 1 year means without any failure, particular product, for example, say mobile is working satisfactorily. And in between that, if it fails to perform its designated function, then companies are normally giving the replacement or free repair. So that is the specified time. And whenever you are likely to increase the value of your product, you have to increase the specified time in terms of the giving the more warranty. And fourth important element is operating condition. So operating condition is like whether they are working under vibration, they are working under temperature, or say specific operation profile. So these are the important elements of the reliability over which we can easily define, or we can easily predict, or we can easily calculate the reliability. Now reliability is basically decided or basically introduced by means of the life cycle curve, and that life cycle is normally uh, highlighted or shown by means of the curve. That curve is called as the bathtub curve. Why it is called as bathtub curve? Because the reliability or life cycle curves are in shape of the bathtub, like this. So it is normally or famously known as bathtub curve, in which three distinct phases are there. Just have to see the first phase is debugging, then chances of failure, second phase is chances of failure, and third one is the wear out phase. So this you have to see this is called as the debugging. Debugging means when you are starting, when you start to perform duty of the product, then this is called say x-axis, and this is say y-axis, x and y-axis. We have to see that when product is start to perform its function, then because of the manufacturing defect, some starting torque are there, some starting vibrations are there, and because of that, infant mortality periods are there. So there is a more chances of the any product to fail in initial level, and then it becomes saturated. So this is the initial condition or debugging period where there is a more chances of infant mortality is there with respect to time, failure rate is decreasing. Then we have to see the constant failure rate, and this is called as the useful life period of any product. This is called as the useful life period, over which without, or we can simply consider it as specified operating condition. Normally companies are giving the warranty in terms of this period. So this is useful life period, and after certain use of the or certain operation of the product, some parts are wear out, and because of the wear, there is a more chances of the product to fail. So this is, they are now entering into the third zone, and third zone is called as the wear out zone. So in which failure rate with respect to time is continuously increasing. So this is the increasing failure rate. The second reason is called as the constant failure rate, and first one is called as the decreasing failure rate, or you can call it as infant mortality. Okay, so this is about the third three part of the life cycle curve that we are considering for understanding of the reliability. So this is, you can easily see that debugging phases are there. So this is about the debugging phases that we already discussed in the previous slide. Then chances of failure or useful life period is there, and third one is the wear out zone, where you have to quick failure rate on y-axis and time on x-axis, and time to draw the diagram. That diagram is called as the life cycle curve for any product, as it is shape of the bathtub, so it is famously known as the bathtub curve. So this is about the life cycle curve. Okay, and we have already discussed these things, and it is usually covered by warranty period, debugging period, and this is the exponential form, or it is called as the constant failure rate, and sharp rise in failure rate, that is the wear, and this, that is because of the fatigue, corrosion, or wear, the kind of thing is there, where chances of the product to fail after entering this region is considerably very high, and normally they are not covered under the warranty period. And this is about the variable distribution, variable interpretation, where based on the beta value of the beta, we can cover how infant mortality is there. Beta less than 1, beta is equal to 1, where an old part is as good as new one. An old part is as good as new one. You can see here. Failure is very random. So old part is absolutely good. No need to replace. Up to beta is equal to 1, and once beta is between more than 1 but less than 4, then low cycle fatigue is there. Okay, and corrosion or some wear out occurs. So it is likely to start towards the failing zone, and once it reaches beta to more than 4, then it enters into the rapid wear out zone, or there is a chance, and then we can put it as, we have here considered the replacement. So new one is better than running on the old part. So this is about the variable distribution based on the performance of the product for understanding of the probability of the failure based on the variable distribution. Now, another important term is maintainability. So here Maintainability, normally we are deciding chances of failure, degree of detectability, and severity. But severity is very simple term, and we are likely to convert the severity into maintainability. Now, maintainability improves what? Normally, we have three important parameters that you have to keep in mind. One is the chances of failure. How a particular product is having the chance to fail. If chances of failures are more, then we can consider it as it is critical part. And chances of failures are less, then we are considering it as less critical part. And second one is degree of detectability. Degree of detectability is how easily we can detect the problem inside the product or inside the systems so that we can prevent the sudden breakdown. Same way, if degree of detectability is less, then it is considered as more critical component. And third one is the severity. Chances of failure. Chances of failure C. Here you can see the chances of failure C. Then degree of detectability, for example, say D, and say severity. Severity means effect of the product or system when it is failing. Suppose a particular system or subsystem or say product is failed, then how it becomes severe to overall plant. So more severe means that part is more critical. Now here severity is to be converted into maintainability in more engineered way. We can consider it as. So maintainability means how a particular component or particular system or particular product is easily maintained based on the S, based on the accuracy, based on the safety, and based on the economy. So these are the four important parameters over which we can easily maintain any component to specific period of time of the performance. So once we can easily define the maintainability criteria or maintainability index, then we can easily find out criticality index of that particular component. So if maintainability is good, then we are considering it as that particular component is low critical. So maintainability is a design parameter or maintenance is a result of design. So if you have to think about the maintenance, then we are easily thinking about the result of the design. We can easily improve the design. We can improve the service process so that accordingly we can improve the dimensions of the product. If any error is there, then obviously we can improve the maintenance. So we are having the less chance of failing the particular component. So this is about the concept of the maintenance. And maintenance is one of the most important part. And maintenance is always associated with the reliability. Whenever reliability is there, maintenance is always there. So for improving the reliability, we can consider it as you must concentrate on maintenance optimization. Otherwise, it is almost impossible to improve the reliability. Now, challenging task is what? Most challenging task is to improve the reliability. And for improving the reliability, we must concentrate on maintenance, types of the maintenance, style of the maintenance, ways of the maintenance. And maintenance is not easy. Before deciding the maintenance of any component, we must reach to the root cause of the failure. Once you are reaching to the root cause of the failure, you can easily identify the problems or causes and effect of the component, why it is failed, and you are likely to try to reduce that type of the failure so that ultimately maintenance or maintainability is improved. And if maintainability is improved or we have smoothened out the maintenance, automatically your reliability is improved. So this is reliability and maintenance is always associated with each other. Now, for measuring the maintainability, we must convert it into mathematical form. Okay, measure of the maintainability, because maintainability is not a word, a theoretical word. It is the mathematical word. And to decide or to define the to measure the maintainability, you must have some parameters that you have to keep in mind before measuring the maintainability. That is mean time between failure. Let us see. Time between the two failures, consecutive time between the two failures. So once you know the MTBF, then you can easily find out which type of maintenance you have to go for. because we have lots of types of maintenance are there. Breakdown maintenance is there. When a particular material is failed, and when it fails and you start to repair it, then it is called as the breakdown maintenance. The second type of maintenance is, for example, civil maintenance, like whitewashing of the wall. That normally we are doing at our home, at a festival season, or say lubrication of any component. That is also a civil maintenance. But third and fourth type of the maintenance is important. That is preventive maintenance and corrective maintenance. And to decide the better preventive and corrective maintenance, we should know about the mean time between the maintenance, time between two maintenance. So for that, you must have the knowledge of the failures of frequency. So preventive maintenance is works on the principle of prevention is better than cure. And corrective maintenance is normally considered as the condition-based maintenance, where you have to continuously measure the condition of any component, any parameter. For example, you have to measure continuously the temperature or the pressure of the boiler, and accordingly, because of the abrupt or adverse change in sudden change in temperature or pressure, we will introduce any failure is there. So corrective maintenance is normally condition-based maintenance. So that is about the maintenance, and maintenance is normally in terms of non-replacement. But suppose you are not maintaining that particular component and a particular component is failed, then you must have to replace them. For example, say brake liners. Then it is called as the mean time between the replacement. Instead of maintenance, we have the another term, that is the replacement. So for calculating the maintenance, whether it is maintained, it is possible to maintain same product or same component, or we have to compulsorily replace. Normally what happens, bearing is one of the most important and most critical component in mechanical engineering and in all major processing industry, where replacement is 100%. But every component is not having replacement in 100%. So depending upon the requirement or depending upon the choice of the or chances of the product or performance or working of the product, we have to decide whether it is going for maintenance or whether it is going for the replacement. Unnecessary replacement will introduce the cost. Okay. So this is about the terms based on which we can easily calculate the maintenance. Now we will see another type of the maintenance. Frequencies of the maintenance that I have already discussed, that number of frequencies of failures are needed for deciding the maintenance and replacement. An unreliable system requires extensive maintenance. So reliability function is nothing but the 1 minus ft, where ft is the probability of the system. Mathematically, reliability is defined as the RT. RT is the reliability, RT is the function. So reliability function is equal to 1 minus ft, where ft is the probability of the system will fail with respect to time t. So fail with respect to time t, 1 minus probability of the failure is called as reliability. For example, say particular component is having the probability of the failure as 10% out of 10 times. For example, say a particular component is failed in one time, then we are considering it as fail probability is 10%. Then reliability is considered as 1 minus 10 means 90%. 1 means 100%. In terms of function, it is 100%. Okay. So if probability of failure of a particular component is, say, for example, 20%, then we are considering RT as 1 minus 0.2 or 0.8 or 80%. A kind of thing is there. So here, by this we can easily convert the reliability into mathematical term, because we must have the knowledge of measuring the reliability. Without measuring the reliability, we cannot introduce or we cannot enhance the system performance. So this is about the characterization of reliability in terms of mathematics. In exponential form, RT is equal to e raised to t minus theta, where theta is equal to mean time between failure, and lambda is the failure rate, 1 by mean time between failure. Theta is the mean time between failure. So minus t by theta, where theta is equal to nothing but the mtbf. So lambda is the failure. So failure rate is nothing but the reverse or inverse of the mean time between the failure. Or simply we can, in another term, we can equating the reliability as RT is equal to e raised to minus t by theta or e raised to minus lambda by t, where 1 upon theta is equal to lambda. 1 upon theta is equal to lambda. Just have to see 1 upon theta is equal to lambda. And 1 upon theta is nothing but the 1 upon m t b and f, mean time between failure for any particular component. So this is about the reliability in terms of mathematics. Now failure rate is what? Lambda. So lambda is nothing but the number of failures divided by total operating hours. For example, say particular component is having total operating hours say 1000 hours, and in between 1000 hours, a particular component is failed 10 times, then 10 divided by 100, so 1 divided by 100 means 0.01% is called as the lambda. That is the failure rate, or we can considering it as 1%. 100 means 10%, and 10 means 1%. So lambda is nothing but the percentage failure rate. Okay, so total number of failures divided by total operating hours. So total operating hours is say 1000 hours, out of which a particular component is failed 10 times for 10 hours, then we are considering it as percentage failure rate is 10%. So this is about the failure rate. For example, say 10 components were tested, the components are non-repairable and failed as follows. So component 1 failed after 75 hours, component 2 failed after 125 hours, third 130 hours, or 325 hours, and component 5 say 525 hours, and so on. Then what we have to do is, or how we can find out the failure rate, that I will show you. This is about the 75, second component, third component. Just you have to see each and every component is there. First component, second component, third component, or the fifth one. 5 failures, operating time, this one. 5 into 525. For example, say 5 failures, number of failures are say 5. And operating hours is 5 into 525. For example, say for component number 5. So 5 into 525, and here you can see that 5 into 525, so 3850. So number of failures are 5 divided by total operating hours, 3805. Okay, 3805. So it is 0.001314. So here you can see component 5 failed after 525 hours. Okay, component 5 failed after 525 hours. So 5 components are there. Okay. Accordingly, for one component, you can find out lambda failure rate. For 2 component, you can find out for 125 hours. Or for 3 component, you can find out, and so on. So on. Here we have calculated for the 5 components, 5 failures. So 5 failures are there, divided by total number of operating hours. Total number of operating hours are 5 into 525. Sorry, total operating hours are we already calculated. Already we have. So just you have to see here how it is calculated. So total operating hours may be any. Here we have decided it as total operating hours. So this is not, here you have to keep in mind that total operating hours may be any. That is given for any particular component. Standard total operating hours is given. and you have to take it as for a particular product or for a particular component, say total operating hours is say 5,000 hours, for example, say, and it is failed 10 times, then 10 by 5,000 you have to put it as. Okay, so that is the failure rate. This is the way how you can find out the failure rate. So failure rate is nothing but the you should have knowledge about the total operating hours and number of failures. Total operating hours and number of failures. Okay. Now second example will clarify more regarding this failure rate. The chart is given, shown the operating time and breakdown time. So operating time is highlighted in green colors. Here you can see operating time is highlighted in green colors and breakdown time is highlighted in yellow color. So we have to determine the mean time between failure. What is the ideal or average mean time between the failure? So total operating hours we have to calculate first. So operating hour is this one, 20.2 plus 6.1 plus 24.4 plus 4.35.3 plus 14.6 this one. So here this is added by mistake. Okay, that was to omit. Then you have to calculate total operating hours as 136.9 for example. Say. Okay, so this is the total operating hours. Now, mean time MTBF is nothing but the reverse of the failure rate. So failure rate is nothing but the number of failures divided by total operating time. So number of failures means first time it is failed, second time failed, third time failed, and fourth time failed. Because downtime is shown all times here. Okay, so here you can see that total operating hours 136.9. And why I have put it as for number of failure for because for time in previous chart for time a particular product is failed and it is going to entering into the downtime. So for by 136.9. So this is the lambda and NTPF is nothing but the 1 upon lambda. So this is the mean time between failures. So every time after every 34.22 hours, this particular component is failed. So what is the reliability of that particular system? So reliability is nothing but the or system reliability is nothing but the R is equal to E raised to minus lambda into T and time T is 20 hours and this we have lambda failure rate is we already calculated. So R is equal to E raised to minus lambda into T. So reliability is 55.74%. So approximately 45% time is wasted here. So to improve the reliability, we must reduce the downtime and time to improve the operating time. So that automatically, suppose you have to improve this one. Now, how we can improve the reliability? Suppose you want to improve the reliability, you must improve the failure rate. Yes. So operating time is to be reduced or reduce the number of failures. So that automatically lambda is increased. Lambda is increased, then mean time between failure is decreased. And mean time between failure is decreased, and lambda is increased. This product will increase and will give the more value of the reliability. So trying to reduce the downtime or trying to increase the operating time so that we can improve the reliability of any product. So this is about the correct understanding of the reliability. Now, whenever we are understanding or whenever we are going for uh, modeling a number of components in a system for actual industry, there are lots of components are there. For example, I will give you the simple example of refrigeration system. In refrigeration system, we have compressor, okay, then condenser, then expansion valve, and evaporator is there. And all these components are associated or joined in series for introducing the refrigerating effect. So for that, suppose you want to calculate the overall reliability of this refrigerating plant, you must have the individual reliability of condenser, individual reliability of condenser, compressor, condenser, individual reliability of function and individual reliability of key operator. So every time, depending upon the requirement in industry, your components are joined in series or sometimes in parallel. So if they are joined in series, if your component is joined in series like we have understood in refrigerating system, then if a particular component is failed, then adjacent component after available or working after that component is, if it is in working condition, they are considered as failed, even if it is in working condition. Okay. So uh, reliability is affecting. For example, say in this case, compressor is working, but condenser is failed. Even if expansion valve is in good condition, but condenser is not working, there is a downtime in terms of expansion valve and condenser, evaporator. But even series, if a particular component is, for example, say in series, instead of series, they are in parallel. For example, say they are working in parallel like this. Then if this component is failed, this particular component or this parallel line is working. So reliability is different. So for joining or arrangement, depending upon the component of the arrangement of the component, whether in series or whether in combination or whether individually in series and parallel, reliability affects. So you have to keep in mind about the relationship or reliability component, how they are joined together, series, parallel, or combination of all, both. Okay, so this is series network. Very simple thing is there. This is series network where we have seen that overall reliability of the system is multiplication of individual reliability, multiplication of reliability of individual component. So this is about the series network, and in terms of exponential form, e raised to minus lambda 1 plus lambda 2 plus lambda 3 plus up to plus lambda n by into t, where t is the total operating time, and lambda 1 to n is the number of component. For example, say, just have to see now the example. System expected to operate for 1000 hours. This system is expected to operate for 1000 hours, and it consists of 4 subsystems in series: system A, system B, system C, and system D. And mean time between the failure of all the systems are given. So you can easily find out lambda 1, lambda B, lambda C, and lambda D by inverting by reciprocal of the MTBF given. And based on this, we can easily find out the reliability. So this is the simple example of system in series, calculating the reliability of system in series. Another example is parallel network. So parallel network is like this, and for that reliability is different. So this is the reliability of parallel system. Have reliability of A system plus reliability of B system minus reliability multiplication of both. So this is the different calculation of the reliability if they are in parallel. So that is the difference. In series, they are simple in multiplication, but here you have to add reliability and then minus of multiplication of both the reliabilities. So this is about the calculating of the reliability when they are joined or working in parallel mode. Likewise, so reliability of the system associated in parallel is equal to 1 upon lambda A plus 1 upon lambda B, or minus 1 upon lambda A plus lambda B. Okay, so this equation you have to keep in mind for calculating the reliability of parallel. If there are in three systems, then series system reliability RS means system reliability in parallel, then 1 minus RA into 1 minus RB into 1 minus RC, and so on, 1 minus Rn, where n is the number of component associated with the associated in terms of associated in pattern of parallel scheme. So this is about the and combination. Here you can see the reliability of A into reliability of B plus reliability of C because they are in parallel. Just go to C. The very important thing is these both systems are in parallel. So this equation is based on the parallel. And outcome of this B and C is in series with the A. So RA into multiplication of all this system will give the system reliability. So combination thing is also there. Combination mode is also there. And here you can see one of the most important things. Two parallel system A and B. So they are calculated separately in terms of parallel thing in another form of the equation. This is the another form of equation. And this is for C and D as they are in parallel. And outcome of both is in series. So multiplication of both. So this is the way how you can calculate the system reliability, whether they are in series or whether they are in parallel. And more complex system may be there. So you can easily, I will give you the example in upcoming tutorial to calculate the reliability of complex system. Okay.